talk of the afternoon. It's a pleasure to introduce Lisanne Taams from, I won't try to pronounce your university. I'm very poor Dutch pronunciation. But her title is on the projectivity of the moduli space of semistable vector bundles on a stacky curve.
Well, first of all, thank you to the organizers for giving me the opportunity to speak here. So I'll report on some joint work with Chiara Damiolini, Victoria Hoskins, and Sveta Makarova. As the title suggests, I'll show that a certain moduli space is projective. So I'll try to answer sort of three questions in this talk. The first one is what? So here I will give you sort of a stacky curve 101, just so that we all know what vector bundles and stacky curves are. Then I'll try to do the hardest thing and answer why. I think there's lots of reasons why, but maybe one of them is like the relation with parabolic bundles, for those of you who study those. And then the final half of the talk should be about the question how. And this somehow has two steps. Step one is apply the existence theorem. So this was the theorem that our last talk was about. And as we heard in the last talk, this is really made for vector bundles. So this somehow is the easy part. And then the second step will be to construct a line bundle explicitly and to explicitly give lots and lots of sections. Okay. So let's get started. Oh yeah, before we start, maybe, so this talk, there will be a field, and let's say it's characteristic 0 and algebraically closed. So if you want every single statement in this talk to be true, you should need this, but ask me if you are wondering what can be generalized. Okay, so let's start with the definition of a stacky curve. We already saw stacky curves in the first talk this morning. So let me write down the definition for you. Right, so for me, a stacky curve really is just a linear Mumford stack, which is a curve and generically a scheme. My curves are not very general, they're very special. They should have all the properties you could possibly give. So, well, they're one-dimensional, they're smooth, they're irreducible, and they're projective. Because this was also mentioned in the first talk, for a curve, projective just means proper, or its equivalent. And so actually we like to think about stacky curves really just as something which looks topologically like a curve, but there's some points, and these points have stacky behavior. And in fact, for curves, this is just a theorem. Namely, all stacky curves are root stacks. So what is a root stack? Well, you start with some curve, which is just a scheme. You pick a point on it. A point defines a map to our favorite stack, which is A1 mod GM. Because this a point on a curve is just an effective divisor. This is the stack of effective divisors. Then there's the power map. Which is the power map on effective divisors. and then we take a fiber product, and you obtain a stacky curve. And so away from the stacky point, this map is an isomorphism. So generically it is a curve. And then at this point, you will get a cyclic stabilizer sort of sitting on that point. And then in general, if you have lots of stacky points, you would just iterate this construction, do it once for every point. You end up with lots of these B mu e's inserted. Okay. So this diagram actually produces for us something nice, because we can take sort of the contraction to BGM. And this provides us with a line bundle. And this line bundle I will call O of 1 over EP. Why do I call it O 1 over EP? Oh, let me call this map pi. Pi is a coarse moduli space map. Then this satisfies that if I pull back O of P, then I get O of 1 over P, 1 over EP to the tensor power E. And as far as I am aware, this is why it's called a root stack, because this is a power. So the opposite of powering is rooting. So that's why we get root stacks. Okay. Then okay, so let me use this inclusions for something nice. So let's call it like the iota of P for some stacky point C, P. And say I have some vector bundle on the stacky curve. Then I can pull back to B mu E. And then through commutative algebra, vector bundle on B mu E is nothing more than a graded vector space. Every graded vector space is of the following form, or is isomorphic to one of these. So I just have the trivial vector space in each degree. So the grades are given by the cyclic group, which is dual to mu E. And these numbers over here are an important invariant of my vector bundle. So these are called the multiplicities. At P. So you can do this for every P. So this sort of important invariant, you can combine it with the others. So whenever you have a vector bundle, you can ask for its rank. You can ask for the degree of the push forward of V. This is some sort of analog of what the degree should be. And you can ask for a big collection of multiplicities. And whenever I have all of this data, I will just call it by some lowercase Greek letter. If you just remember, this means take lots and lots of invariants. And then these invariants allow us to construct nice moduli spaces. So I will define M beta, which is the moduli stack of vector bundles with invariance beta. And this is sort of the main player of this talk. Okay, so these are vector bundles, these are their invariants. The word semistability appears there, so I should probably tell you what that means. So for this we start with a generating sheaf. So these generating sheaves are the ample vector bundles we saw this morning. We need something slightly weaker than ample, but this can be summarized as saying that all the multiplicities at any point is strictly positive. This is sort of saying that, yeah, once you pull back to the stacky points, you will have all the possible representation that you can get. Then using a thing like this, we get the E degree. So the E degree of a vector bundle, which is defined as the degree of some horrible formula. I'll write it for you. So we can define this E degree. The reason this E degree exists somehow is because this is what shows up in the Riemann-Roch theorem. If you try to do Riemann-Roch for stacky curves, you want to put a degree somewhere, this is the thing you should put there. So then this defines an E slope by simply saying that the E slope of V is the E degree of V divided by the rank of V. And then, as always, we say that V is semi-stable if whenever we have some sub-sheaf, the slopes are smaller. So this is E semi-stable. So this really depends on the bundle. So semi. Yes, for all sub-objects, we should have that their slope is smaller. Okay, so I say this stability condition depends on the bundle. Actually, it only depends on the multiplicities. This is something nice to have. You can, yeah, these are annoying computations, but it ends up only depending on multiplicities. Then I'll quickly give some notation. I say the bracket between two vector bundles A and B is from A to B minus x from A to B. Right, this is the thing from Riemann-Roch. And then I claim that by Riemann-Roch, this inequality holds if and only if this inequality holds. So this is a way to not work with this formula and just be like, okay, we will just use these expressions to do all of our computations. Okay, so these are the stacky curves, their vector bundles, and semi-stability condition. So this M beta now gets a substack, which I will call, so I'll just write, instead of E, I'll write some invariance, because we remember that semi-stability only depended on the multiplicities. So these are the alpha stable bundles sitting inside of all of the bundles. And this is the one I claim will admit a projective good moduli space. Okay. So, okay, I think we now know a little bit about what, so I'll try to say something about parabolic bundles. There's a really easy way to turn a vector bundle on a stacky curve into a parabolic bundle. So you start with some V on the stacky curve, then you push forward V to the core space to get some vector bundle, and then inside of there you find these twists by this sheaf that sort of canonically exists, and you can like keep doing that until you end up with that one E times, and then by the formula I gave you, this is actually just pi star V twisted down by P. And this filtration defines for you a parabolic bundle with a parabolic structure at P. right? And then I have a claim. Say we'll fix all the things you should fix for parabolic bundles. So we will fix some points inside a curve, some parabolic invariants, which I'll also denote by beta, and parabolic bundles come with weights, so you should fix the weights as well. Then I claim there exists a stacky curve invariance and a generating sheaf. Such that M E semistable beta is isomorphic as a stack to, let's say, like parabolic bundles with respect to the weight B primes, like the stack of parabolic bundles. And the functor is exactly this one. So there's a bunch of things to check. First, you should check that you actually have this map without semi-stability conditions. That's actually also true, and then actually preserve semi-stability conditions. So this somehow means that, like in the 80s, it was sort of proven that this has a projective moduli space, at least over the complex numbers. And I kind of want to say that this method does a little bit more. So we don't just have the existence of some moduli space. We actually will produce very explicit sections of a very explicit line bundle, which means that this becomes a much more constructive approach to understanding these moduli spaces. Another sort of reason to like this is because somehow vector bundles and stacky curves behave much more like vector bundles than parabolic bundles do. So at least to me, you can usually just try to copy over proofs and then more will happen, but the ideas stay the same. Okay. So that means we've reached the how part. So yeah, let's do step one of the how part, which was to apply the existence theorem. So yeah. So this stack of semi-stables satisfies all the criteria of the existence theorem. I will not check all these criteria. Somehow, if you know how to do this for vector bundles on a curve, you also know how to do this. So I'll leave that out of this talk. So what we get proper finite type algebraic space together with a map. Which is a good moduli space map. So I mean, this is really nice, but I don't like proper algebraic space. I would like projective scheme. So how do we do that?
Wait, I have a question.
Yeah.
Even though you said you're not going to tell us about it, could you say it now, right? I mean, do you use affine Grassmannians and stuff to check the criteria?
What do we use? It's kind of just really explicit. You can just write down what S-equivalence means, and then you can be like, oh, it works.
Okay.
Yeah.
Oh, okay. Okay. Oh, yeah. Okay.
Mhm.
That works.
Yeah. Okay. So So what do we do? Well, we want to construct some sort of line bundle on here. And we want to construct so many sections that this line bundle will induce a map to projective space. And then because projective space is an algebraic space, it will induce for us a map. And then what we'll do is we'll say, well, actually there's so many sections that this map has to be finite. And because this is proper, we have a proper finite map, and it follows that this guy is projective. So from now on, it's really just an exercise of finding sections of this line bundle over here. Okay, let me write the line bundle down for you. It's called the determinantal line bundle. There's some input. I take some V, which is a vector bundle on the stacky curve, such that V pairing with data equals 0. You don't strictly have to do that to get a line bundle, but to get sections, you should probably want to do this. Then I have L of V. I'll not write down the line bundle, I'll write down all of the fibers for you, and then we'll just hope that they glue. So say I have some bundle inside of M beta, then I provide for you a one-dimensional vector space. Which is the determinant of a certain complex. So what is the complex? It's just this one. Yeah, so these will define some fibers for me, and then actually, sort of because it's the determinant of this, you maybe have to convince yourself that it actually glues, but it does. I have 5 minutes at the end now, I can talk about the gluing. Oh, sorry, yeah, there's no on this one. Thank you. Yeah, so actually, because of the construction, it actually comes immediately with at least one section. It's a good start. Namely, we can take the determinant of delta. So this makes sense because by assumption, over here, these have the same dimension, so we actually get a determinant map. And this, yeah, this really is side of LVF. And then the question is, what really is this section? So maybe, so I wrote delta, but this is just the zero map. So then you have to wonder what's the determinant of the zero map. Well, there's two options. If this hom VF is non-zero, then the section vanishes there. It's just a zero map between some vector spaces. But actually when the hom itself is zero, this is a zero map between two zero vector spaces. So then the determinant is 1. So we've constructed a section which vanishes exactly on the sheaves where hom VF is non-zero, and it is non-vanishing whenever this hom is 0. Okay. So that's one section down. Now we need to find lots more sections. So there's one sort of key point here. the following, that say we have some exact sequence of vector bundles on curly C, then this induces also something on the level of the line bundles, namely LV is just the tensor product of the other two. So this really is just because the determinant behaves well with short exact sequences. And then I guess a special case of this is that if you take a vector bundle, sum it up a bunch of times, then this is the tensor power of the original one. But the point here is that now this bundle LV, it only depends on its class in the Grothendieck group of bundles. But on the other hand, the section does depend on V. Right, so what this means is that if we can vary V within the same class, then we get lots of different sections of the same line bundle. And so the last 10 minutes I will tell you how to find lots of different V of the same class so that we get lots of different sections. Are there any questions so far? Okay, so I'll not prove the full statement for you because I can't do that in 9 minutes. But I'll prove a weaker theorem, which is sort of, the proof really shows the spirit of how all the technicalities will work. So this is semi-ampleness on the stable locus. So what does this mean? This means that my line bundle defines a map to projective space on the stable locus. So I'm not saying anything about finiteness, just that there is a map to start with. Okay, so this is the theorem that we will prove. So we start with some generating sheaf, which is our stability condition. We ask that the pairing is 0. So you can always manipulate your generating sheaf without affecting the multiplicities and guarantee this. So this is not a condition, this is just to make the theory of the line bundles work. And I say then there exists some large M, which is effectively computable. Such that for every single bundle inside of M, alpha semistable beta, there exists some V inside M times alpha, so these will provide sections of the mth tensor power of our original bundle. Such that everything vanishes. So this equality is by assumption, and this is what we're going to show. And then actually, It's not just there exists a general V, it will do this. Right, so actually we get a very large set of V's which will provide the correct sections. Okay. So proof. Let's say we have a V that doesn't work, so apparently it's not general. So take any V with a map to F, which is not the zero map. Let's call it little f. And let's assume first that it's not surjective, so that we get a short exact sequence. I will write some invariants below everything, so I'll just call the invariant this gamma. This has invariant M alpha by assumption. This has invariant M alpha minus gamma, because it fits in the short exact sequence. And then, yeah, so I say semi-stable. I really mean stable now. So we now know by our assumption on stability that this is less than alpha beta, which is 0 by assumption. This is the slope condition. So now I can write down some nice stacks for you. Namely, there is the stack of all vector bundles which have the same type as this one. Then I take the stack of all vector bundles with the same invariance as this one. And I take over this the stack of exact sequences. So this is the stack of sequences which look like this. And then you can take the projection on the middle part, and then you land in the stack with the correct type. So now all of these have very easily computable dimensions. So maybe from deformation theory, if we remember, these for classical curves, the dimension is x minus Holm. Same holds here. So these dimensions are actually given by these brackets. What's the dimension of this? It's the same. And then if we think about the dimension of the fibers here, these are actually given by an extension up to automorphisms of extensions. So that is actually, do the order correctly, also given by a nice bracket over here. And then what's really nice about this is that this map is representable. So this is somehow easy to see, because if you have a short exact sequence where there's a map of short exact sequences where the middle one is the identity, then everything becomes the identity. So this is a representable map. And that means that I can talk about the codimension of its image in a nice way. I claim that the codimension of the image, I just have to add and subtract these all up. And then I find that it is given by this formula. So the M actually pops out. So what I now know is that this V, which had this map, lies in the image of this map. But this image will have arbitrary high codimension, because this is negative and I can choose M very, very large. So that means that all the V's that don't work lie in a very high codimension thing. So 2 minutes, I'll just do the version where the map is surjective. So then the image of F is just F. This invariant is just beta. Over here, I don't have to do the full moduli space because I know what F is. So this just becomes B of out of F. So this is the moduli space of F. And then you see, okay, this gamma gamma gets replaced by dimension of the automorphism group of F. This becomes alpha beta, so this is just 0. And we know that every vector bundle has at least one automorphism, so this is again positive. So we know that all of the bad V's lie in high codimension subspaces, and therefore a general V will actually provide a section doing what we want. Okay, I'll end there. Thank you very much.
Are there questions for Lisanne? Yes, sorry.
So you have more invariants for vector bundles, right?
Yeah.
Rank 3 and multiplicities.
Yeah.
These now give you the connected components.
Yeah, so actually these are also irreducible. You can add to. Yeah, they're irreducible whenever they're non-empty. Yeah.
What happens if you try to extend this construction beyond dimension 1? I'm not quite sure where dimension 1 exactly is crucial in this.
Well, in dimension 1, everything is smooth. So I don't know, pretty much all the properties of this diagram break.
Right.
Yeah, pretty much all of them.
But I presume you can probably still talk about stacks of torsion sheaves on higher dimensional varieties and some sort of stacky devices.
Yeah, this does exist, but I'm really not an expert. I think about curves.
Okay.
Yeah.
Thank you.
Yeah, also the construction of the section using the determinant line bundle won't carry over to
Okay.
surfaces.
Yeah, I guess you have an extra X group.
Right. Okay.
Other questions?
So, do you think, instead of going in the direction of changing the dimension, how about allowing moderate singularities on the curve, such as nodal?
I know some people think about this, but I never
You
had.
haven't.
But yeah, but I know a lot is still possible. Yeah.
Yes.
So we know a lot of things about the moduli space of parabolic bundles. And
Yes.
so all the geometry, automorphism rules, Radboud terms, everything translates.
Yeah, I mean they're the same stacks.
Right.
So you just have to be a little bit careful because somehow the stacky curve you end up with does not just depend on the parabolic points, it also depends on the invariance. So sometimes your correspondence is a little bit strange, but as the spaces themselves we understand somehow the same.
Maybe now, so where, like, defining the E degree, I mean, they don't really need to generate a sheet, right?
No, so for about a lot of things don't really require generating sheaf, but if you want the full theorem, at a few points it matters. But actually, if you know about parabolic bundles, this E degree under the correspondence becomes the parabolic degree. And if your E is not generating, that's like considering a parabolic degree where some of the weights are 0. Or like some of the weights collide. So this is somehow a degenerate case.
You mean E when you take E to be trivial?
Yeah, that would be like where all the weights are 0. So it's not really a parabolic bundle anymore then.
Is this theorem that you've written here sort of generalized to give a characterization of semi-stability? Does it hold
yeah,
for semi-stability in the converse?
The converse is there as well. It's like, yeah, when you're semi-stable, you get a bundle, but if you have a bundle, you're also semi-stable.
Can you translate that into a condition for semi-stability in the parabolic setting?
Oh, I haven't tried yet. I wouldn't, like, off the top of my head know how it works right now, but yeah, I guess you should be able to say something, but yeah.
Other questions? Well, if not, let's thank Lisanne again.